Glad to see you've come back for round two. So we are talking about finding volume with cross sections here. The first video from this lesson talked about squares and then showed you how to adapt that to get rectangles and triangles. So just to kind of give you a visual on that before we move forward here, because I've got my GeoGebra open again, I could make this a rectangular cross section. This thing here is to say, you know, what that ratio is, what that K value is. The one example we did, we made the rectangles 3 times higher. And so you can see that just makes a taller solid. And so it ended up, you know, taking our area and just multiplying it by 3. Okay. But now what I want to look at is circular cross sections. So this is example 1. If we flip to the next page here, this was that sine of 2x function that we started with. And now I want to look at a circular cross section. So taking a look at that, again, it's like you've got just kind of a disc wedged into the board there. That's what we're going to build our figure with. So our solid has more rounded edges, something like this, okay, that we're trying to find a volume of. Okay, so we need to think about how we're finding area of a circle. Well, area of a circle we know is pi r squared. We can fill that into our table here. Now the question is, what's r? So remember when we were doing squares, we took this purple line and we said this purple line is f of x minus g of x, right? But what I want you to notice here is that that purple line is not the radius of the circle, it's the diameter. So we need to think about how do we then change that so that it becomes a radius, okay? And that is where this thing gets a little bit uglier. I'm going to turn this so I'm not writing weird and slanted like this one. But when we're talking about circles or semicircles, okay, the diameter is f of x minus g of x, which means the radius is f of x minus g of x divided by 2. We'll write that nicer over on the other side. I didn't leave you much space to jot that in. But the radius, we have to take this diameter, this f of x minus g of x, and cut it in half to make r. Okay? The nice thing is, just like up here with the 1/2 and the k, pi is a constant. Okay? So when I write my integral, it's going to be pi times the integral of r squared. And then again, it's just a matter of thinking about what is r squared. Here's r, right? So in our final integral, we're going to have pi times the integral from a to b of f of x minus g of x, all divided by 2. And that dividing by 2 is happening before the square. I would really recommend writing this down on paper first before you start typing, okay? Or into a calculator, into Desmos, whatever it may be, because getting this set up right on the fly is hard. You want to write it and make sure that the dividing by 2 is happening before the squaring, okay? So then real quick, how do we get semicircle? If we know the area of a circle is just pi r squared, a semicircle is just half of that. And the nice thing is that half gets to just go live outside with the pi. So we could really write this as like a pi over 2 because all of this is a constant, right? It's a coefficient, I should say. So a to b, here's my r squared. And so then this will be pi over 2. This one gets to divide by 2 twice with the pi and with the r. F of x minus g of x divided by 2 squared. Okay, so you've got all your real basic formulas. Can I promise you these are the only shapes you're going to see? I mean, probably. I've definitely seen problems that throw you some curveballs, but if you know how to find an area of whatever shape it is you're talking about, then you can figure out how to write your integral. I'm thinking of one problem in particular I know I've done during our practice time where it's an FRQ and the cross-section is some weird shape. Like it's not a defined geometric shape. But the problem gives you an area formula. So all you have to do is take that area formula and plunk it into your integral. Okay? So whatever shape you're working with, find that formula first, put it inside the integral, think about what you need for that formula and how it's defined by the graph. Usually it's f of x minus g of x some way, somehow. Okay? Okay, so let's head back to example 1 here. We did this one in the previous video, but now let's do it with circular cross sections. Let me get my graph back up here so we can see it. It was 2 sine x. Oh, I'm way zoomed in. There we go. And we were going from 0 to pi. We're looking at this area right here. So we know that we're going to do from 0 to pi. And we want to do pi times the radius squared. Now my radius is half of this distance from here to here. We said this distance is just 2 sine of x. 2 sine of x minus 0, right? And again, I'm going to write that for emphasis. We don't really need the 0. But 2 sine x minus 0 divided by 2, and then all of that squared. So here's my radius, f of x minus g of x divided by 2, squared with the pi out front. Okay? Let's see, I didn't name it f of x. I should have, because that would make this easier, but that's okay. I'll make it work. From 0 to pi, over here, we're doing 2 sine x minus 0. Again, I know that's dumb, but doing it for emphasis so you know that if there were another function there, this is where you would subtract it. Divide it by 2, square it, dx. And there is your volume with circular cross sections. 4.935. Now, going from circles to semicircles is not hard at all. Okay, circles to semicircles, the only thing that's going to happen is basically this number is going to cut in half. We would show that in our integral by making this either a 1/2 pi or a pi over 2. In Desmos, I'm just going to go over here and divide that by 2. And we end up with 2.467. Okay, so we've covered all our shapes. The only thing left for us to talk about now is integrating along the y-axis as well as the x-axis. Okay, so let's talk about example 3 here. Okay, I guess before we start example 3, and by the way, I'm going to leave off example 4. Example 4 is kind of crazy. So we may do this in class as a challenge when we do sort of our AP test review time. Right now, when we're just trying to learn the basics, this is probably a little excessive. So, okay, so when we're integrating, when we're building these cross sections, what we've been doing so far is building cross sections that stack alongside each other like that, right? So we integrate from left to right. We integrate along the x-axis. We can also build cross sections like this, okay? And in this case, we're going to integrate along the y-axis. Now, most of the time, the wording on this talks about being perpendicular to an axis. So like, for example, these cross sections are perpendicular to the x-axis. Excuse me. Perpendicular to the x-axis, so we integrate along the x-axis. These are perpendicular to the y-axis, so we integrate along the y-axis. My wording on example 3 flips that up just a little bit. It talks about being parallel instead of being perpendicular. I don't love that. I think the wording you're going to see more often is perpendicular, but we'll run with it for now. So the one we already know how to do is this one. Parallel to the y-axis would be these cross sections, right? Parallel to the y-axis would look like this, because my y-axis would be over here. So I know that I'm integrating. Let's see, my two functions are, and I'm doing square cross sections, so I'm just going to square this. X squared minus x to the 1/3 squared. I know that's what my integral is going to look like. I am going to have to use Desmos to figure out what my endpoints are. I think this is another pretty boring one. But let's see, x squared. Oh, I should probably do f of x equals x squared And then g of x equals x to the 1/3. So again, I'm looking at this tiny little like teardrop space. This is where I'm going to build my solid, another tiny shape. Okay. And so my endpoints running along the x-axis are 0 and 1. Oh, forgot dx there. And so I can integrate 0 to 1, f of x minus g of x squared dx, and I get a volume of 0.2. Okay, so our next question here is having us integrate this way. It's having us integrate left and right. It wants the cross sections to be parallel to the x-axis. So we're stacking them like a stack of pancakes. Okay. And so we're going to integrate along the y-axis. That means our integral, it's going to have y endpoints, and it's going to be a dy down here at the end. Otherwise, I'm going to use the same setup. I'm going to subtract the two functions and square it. My endpoints on this one do come out being the same. That's not always going to be the case. It's just because I gave you a really boring one where it's 0, 0, and 1, 1. So on the y-axis, I'm still going from 0 to 1. I sort of wish I'd given you one that had different endpoints. But so this is still 0 to 1, but that's not always going to be the case. Okay. The big thing here is that this distance is no longer f of x minus g of x. Remember, when you're integrating in terms of y, we have to turn the equations around so that they're x equals equations. And so the x equals equations we would write as f of y. So, for example, the x squared function, I could rewrite that as x equals the square root of y. Notice how that highlighted that green part here, right? That red function. This one is kind of weird because the square root of y only gives me the positive side. I don't need the negative side for this problem, so I'm not going to worry about it. But if I needed to use this side of the function, I would just have to do another one with a negative in front. And then if I have y equals x to the 1/3, and I solve that for y, that's going to be x equals y to the 3rd. Raise both sides to the power of 3. You'll notice that blue one just sits right on top of the purple one because they're the same function. Okay. So my integration, and I really don't, I mean, the blue one is technically on, from the y-axis going left to right, the red one would be the bigger one. So I'd be doing the red one minus the blue one, but really doesn't matter if you're going to square it in the long run. So square root of y minus y to the 3rd, and then all of that squared because you're still doing side length squared. Okay. I want you to notice something about the answer here. And this, quite honestly, caught me off guard a little bit when I first started teaching this stuff. I didn't define these with a name, so I'm going to have to just type them in again, which is not too bad. Squared, whoops, sorry about that. Squared, and then don't forget this one needs a dy instead of a dx. This is not the same answer. 0.198. Now, it's awfully close, and I think it's only close because this figure is pretty symmetric. It's a pretty boring figure overall. But you can make these where going in terms of x versus y is a very different volume. And that really threw me off at the beginning. I thought that, we were doing something wrong. But the distances left to right are not necessarily equivalent to the distances going up and down. And so you're not building the same figure. This would create two completely different solids if I tried to do it, if I tried to build this thing. So just know that if you take the same functions and you integrate in terms of x or y, for area, it should be the same no matter what, because you're always just talking about this area. But when you're talking about volume and you're building into that third dimension, the volume will change. Okay, that should be enough to get you started with these. Like I said, we'll have time in class for us to go over some more of these as well. Give these a try. You have a homework assignment that I think has like 5 problems or so on it. Do the best you can, and we'll see you in class next time I see you.